more tinkering update. So right now I have my script controlling my stepper motor so that I can manually do fixed angle rotations per keystroke depending on if I want it clockwise or counterclockwise. So I'm going to show you here. I have the motor. I don't know if you can see, but there is a little piece of tape that is right there. So we're going to call that 90 degrees right now. So if I turn on my script here, it's already plugged in. I'm going to do clockwise 90 degrees. And then counterclockwise. And it's back to the same. So I plugged in my magnetic encoder, the angle encoder on the back here. Readout says start at 272.64 degrees, went forward to 275.71, and then back to 272.72 degrees. So that's like a 1/10 of a degree reported angle difference from the start to the stop, or I guess going clockwise and counterclockwise. So it's getting a little more accurate, same angular velocity each time. And yeah, I'm gonna just keep iterating here. It's Saturday, by the way. It's like 15 till 5. So the goal obviously is to get this to be able to oscillate between a fixed angle, kind of like I've said in previous trash throwaway vlogs here recently in the last month or so. So like if I wanted to go between -30 and 30 degrees, if 0 is like where 90 degrees is on this protractor, go between -30 to 30, sweeping out an angle of 60 degrees every time. We need precision here. We need accuracy, because if it's off by a little bit and then it's eventually, gonna have a net angle that it's like, if I'm just having it rock back and forth and then it's eventually gonna just be like many degrees off, okay, it's gonna knock the coil off. So I don't want that, and I don't want to have to reset it a lot in between. So that's the goal. I'm gonna keep cranking it out here. All right, so it's now 7:47, and I've been tinkering with this for a few hours. My stepper motor, that is. Several problems. Okay, one, I'm really coming to the conclusion now that I can't oscillate directly with the stepper motor, okay? The problem is that stepper motors inside have these 4 coils, okay? And when I change direction, there's going to be, for lack of a better word, interference from the previous direction of motion in the control of going the opposite direction. Like there's going to be residual electromagnetic energy in the motor. So if I say to the motor, in principle through the code, go 90 degrees clockwise. Clockwise is kind of like the default direction, okay? So it's like more accurate, more precise when I go clockwise, okay? But then if I'm like, okay, go counterclockwise 90 degrees, there's still going to be energy essentially in those coils in the motor that will interfere with the signal coming from the driver, let's say, that is instructing or controlling the motor to then go 90 degrees counterclockwise. Okay, so that 90 degree counterclockwise movement is not going to be exactly 90 degrees. Or if I wanted it to be, I would have to have more of a delay in between changing directions, something like that. And vice versa for starting off counterclockwise, going clockwise. There's that residual energy. Also, I kind of mentioned in another video that there are 2 modes for the driver chip. So I'm using a TMC 2209 from Adafruit. There's 2 different modes. There's UART mode, which is basically you're sending digital signals from like the Raspberry Pi over GPIO that you're controlling the chip with. Okay, you're sending digital signals to the driver chip, which is driving the motor, which in principle could be more reliable, but I've found, obviously, if you've been watching these last episodes, there's only one UART pin basically, so I have to add a voltage divider in order to get 2-pin UART mode, or I was trying to solder the bottom of another brand board of a TMC 2209 chip breakout, whatever. So 2-pin UART mode, 1-pin UART mode, it's not happening. But I was able to get this motor to at least do clockwise or counterclockwise movements with what's called standalone mode. So there's 3 pins for that one, and it's analog control basically. So you're sending analog electrical signals in order to control the motor. So there's like a step pin, an enable pin, and a direction pin. So the other problem with trying to go back and forth between clockwise, counterclockwise movements of the motor is I feel like the voltage, in order to be going counterclockwise, has to be either like, let's say clockwise is positive 1 volt, counterclockwise would then correspond to negative 1 volt. It could be that one of them is like 0 volts and the other one is 1 volt, but either way, there has to be like an analog differential voltage difference in order, like you're applying that to that direction pin in order to signal to the motor go counterclockwise instead of clockwise. So if I'm intending to do oscillations of this motor, that's another kind of like interference. That's like a little bit of a problem, or it's an error point or whatever you want to call it, that makes this whole like goal of mine to have oscillatory motion of this motor harder to achieve in practice. Okay, so another problem is I mentioned I have a magnetic encoder. Magnetic angle encoder, I guess, is like the full term of art to use for that. But there's basically like I put a little button magnet on the back metal axle of the stepper motor, and then I made a 3D printed attachment for the magnetic angle encoder board with the chip, so that the chip is right above that little button magnet. It's only like a few millimeters away. You could look up the EM mechanism principle behind how it works on another video right now. If you really wanted to, I could talk about it later. But basically, I was trying to troubleshoot this motor and be like, okay, if I have my control of the motor and then I have the output in code, like it could provide a terminal output of saying like what angle the motor axle is on, then I could more finely tune this motor control basically. So like in principle, or my goal was I'd get an output from the motor and it would say, okay, you're at 0 degrees. Now I'm going to apply 90 degrees clockwise to the motor. And then I would get the output. Maybe it's like 80 degrees, maybe it's 110. And I'd be able to like, use that to troubleshoot my control script. That way I press a key and it's like exactly 90 degrees. Likewise for counterclockwise. But then it's kind of like with the EM energy still being in the motor, in between, not just, clockwise, counterclockwise, but just repeated motor movements. That magnet, the little button magnet, is probably getting like magnetized slightly by the metal axle, because the coils are, around the axle, it's moving the axle, it's magnetizing the axle, most likely because it's like you have live coils, metal axle, what do you think is going to happen? So the magnetic readout hasn't been accurate. It'll be like, it's pretty much only good for seeing whether or not my motor axle returns back to the same initial position. So I would have my control script and I would be doing like 90-degree increment movements in one direction. And then I would just read whether or not I get the same angle output from my magnetic encoder to say, oh, well, maybe it took like actually 6 movements that I was intending for them to be 90 degrees, but then it turns out that because it took 6 of them, each movement corresponded to 60 degrees. So I would tweak the script a little bit so that it's like, okay, what used to be one key press and I know it's 60 degrees, that corresponds to a certain number of steps in the motor. That's why they call it a stepper motor. Now I know what 90 degrees is going to be, how many steps that I have to tell the motor to do in order to do the angle that I want. But then it would go back to, okay, now I've got, the clockwise direction figured out. Then counterclockwise would not be as expected, and I could not converge on being able to say, okay, I'm going to press the P key on my keyboard, it's going to go 90 degrees clockwise. Press the Q key, it's going to go 90 degrees counterclockwise, and it to be just like consistent. And you could just press P or Q, any variation, you don't need delays or whatever, and it'll just move the motor as intended. Couldn't get it to work. And also, if I did just one keystroke, it wouldn't say 90 degrees. In between runs, like I would run my test script, and let's say that like the angle that was being reported was like a change of like 10 degrees. I'd go back without changing the script actually. So I'd run the script, it'd say 10 degrees, stop the script, immediately rerun the script, do the same movement on the motor, and the angles reported by the encoder would be different. So the initial angle, because I would basically like sample from the encoder at an initial angle. It would do the movement, and then it would sample the end angle and try to calculate what the change in angle was during that movement. And it goes back to the whole like the metal axle and the residual EM energy in the motor would basically like throw off the calibration of the magnetic encoder in between runs. So then it would get more complicated, or just, not performing correctly when I would be thinking like, oh, I'm going to try to use the encoder to try and, fine tune oscillating clockwise, counterclockwise with more fine-grained control. So where this is all going, okay, I need to 3D print a Scotch yoke. And I'm going to show you guys this. Okay, this right here is cardboard, some bolts, and some nuts. And this is an implementation of a 4-bar crank rocker mechanism. So this point right here would represent the axle of the motor. So the motor will be spinning here. And the output is this one here with the Amazon Prime tape on it. So basically, the motor will run in one continuous direction. Okay, I'm gonna try to, this is like, coordination, rub your head, pat your stomach at the same time deal. So you see how the output arm with the tape on it is oscillating between some angles. So by changing the lengths of these arms here, you can change the angle that the output is oscillating between, okay? But the problem is that from basically like here to here, the arm is moving faster than when it's moving from here to here. So you go fast, and then you go slow, you go fast. So a crank rocker is not the solution that I want right now mechanically, because I want my oscillation to be constant magnitude of angular velocity. Okay, so the point down here, this is where basically it's like the speed of what I want my magnet to be going through the coil to be. Like if I would have gone with this, then the motor's here, this arm would be, it'd be like vertical. It'd be like this, okay? And, whoops. And the protractor arm here, I'm gonna actually give. So you can imagine this is like my giant protractor with the magnet at 90 degrees shrunken down. It'd be like this, okay? So it'd be oscillating back and forth while this output arm is kind of above it. Like you could kind of visualize, okay, this swinging here. So the output arm would be upwards instead of downwards. And I've got it attached right now, the real deal, okay? See why I call it a giant protractor? I just have it kind of bolted in to my coil so I could figure out the height, whether or not I can fit all this stuff on this retort clamp stand, okay? So now what I'm gonna do is 3D print what's called a Scotch yoke. So it's kind of like a 4-bar crank rocker mechanism, except it's going to have constant velocity of oscillation. One direction of swinging isn't going to be faster than the other. Bless up, because I literally just like drag and dropped a schematic with the dimensions of my stepper motor into AI. And I was like, draw me up a CAD drawing of a Scotch yoke mechanism that's adjustable so I can adjust the angle that it's going through. And I'm going to 3D print it. And it actually did that. So I renewed another month of my membership at the Makerspace, where I can use the 3D printers there. It's like $30 a month, but then it's like only a few bucks to, like, it's super cheap to actually use the 3D printer. So it's like basically I'm writing off the cost of this new attachment as like $30, which is totally worth it. And once I have that, then I can use, since I at least know that the magnetic encoder can get somehow a read of a full rotation by knowing whether or not it returned to the original angle or not, then I can probably get a good readout of what the actual angle is effectively on the output off of the Scotch Yoke. So I renewed that. I've got my badge for that, so I can get into the building tomorrow, because it's like only open to the public on certain days if you don't have a badge that works to get into the, like a little proxy thing to get into the building. So tomorrow I'm going to crank it out. But tonight I kind of want to get a few more things done. Well, one major thing, which is I want to measure the magnetic strength of the magnet that's going in and out of my coil. And that way I've already got the resistance of my coil. It's like 1.6 ohms. I know how many winds it is. And then the only thing left after measuring the magnetic field strength of the magnet that I'm using is to know the speed that my motor is swinging the magnet through the coil. Because I also know obviously the coil dimensions, but then if I have the speed calculations, the resistance, magnetic field strength, then I can use the known Faraday's law of induction to make an experimental prediction of what the induced current is going to be through my motor, or through my coil, excuse me. So that would be all the pieces and parts from like a science perspective of having this be like an actual experiment. Is like, it's not an experiment if you don't have a prediction, and then you've made that prediction before you do the experiment. You get the results. How accurate, how close was your prediction to the results that you observed? So once I measure the magnetic field strength, I'm going to do that with my Hall sensor, which I used for the coil winding jig. Once I measure that magnetic field strength, then it's unknown what speed I will be swinging that through the coil. I also need to figure out, once I get that Scotch yoke on, what's the max and min angle to have the Scotch yoke set up to oscillate between, so that I can have a continuous readout of induced current, magnetic field strength inside the coil, and the angle that the motor is on. Because if it swings past that, then there's going to be, flat spots in my experimental data purely due to the magnet being too far away from the coil. So not knowing that angle is going to have to wait until I can have the full setup, and then just like do a few, manual oscillations and observe where those dead spots are. But then after that, it's just a matter of changing the speed of the motor. So I honestly, also, I neglected to mention that I would probably have to put a Hall sensor inside my coil. That way I can have the readout of the magnetic field strength essentially like relatively inside the coil, basically, as the magnet is swinging through. Because I haven't actually like attached that yet, but it's like I have a lot of the pieces and parts, pretty much everything except for that Scotch yoke, right? So now that I've got my membership to use the 3D printer, I can print that tomorrow or this week or any time in the next month. Spend a few hours on the weekend, go in there, bring a book, and wait for it to print. And it's getting closer. It's getting a lot closer. It's like I've gotten to the end of trying to do it, getting my experimental setup just purely with control the motor with the driver, with the code. It's like apparent now that I also need the Scotch yoke. So as long as I can mount it on my 15-inch tall retort clamp stand, then we're in business. So it's coming together slowly but surely.